So, okay, good morning. I have a lot to tell you. I want to talk about the linear spaces of matrices and the problem I've been most interested in the past 5 years and more generally for maybe 25 years. But it's a very general topic in the sense that it emanates from lots of different backgrounds and motivations. Understanding such spaces, and I'll start with one of the nicest places in which it arose, which is in the context of optimization, Edmond's work. Then I'll talk about several different ways in which it comes up in algebraic complexity theory. Then I'll talk about tensors and graph theory motivations, and at the end, things that at least closer to what I'm trying to do now with these questions related to invariant theory and non-commutative algebra. But the problem, and the concept and the problem are extremely simple. So let me start from Edmond's work. So as usual, just ask questions, whatever you have. Okay. Right, so Edmonds, one of the pioneers of optimization and algorithms and complexity, in fact, wrote a paper in 1967 in which he suggested an algebraic formulation of the perfect matching problem. So I'm talking about bipartite matching. It will be also something for non-bipartite. But if you have a bipartite graph, and vertices on every side, then a very natural way to describe it is for its adjacency matrix. If this is B and you put here the vertex on B here, and you put 1 if there is an edge. 0 otherwise. Okay. What would be an algebraic formulation of the question of whether there is a perfect matching in the graph? Well, G, let's put it in reverse. G has no perfect matching. If and only if the permanent G. Let me write the formula for the permanent question, yeah? No. The formula for the permanent, because we will talk about the permanent and determinant soon in more detail, but the permanent of a matrix, the N of a matrix, of an N by N matrix of variables, J, is simply like the determinant without the sum, so the sum of all permutations in Sn very important polynomial. This is obvious, right? The permanent just count the number, they just count over all diagonals, which are perfect matchings, and multiply the values there. So if you see all of them are 1, you get a non-zero, otherwise you get 0. But the next suggestion, as he probably understood or thought, this is a hard polynomial to compute, so it's not very useful, right? I mean, we have algorithms for perfect matching. That's not an alternative, really. But then he suggested to build another matrix, another algebraic formulation. Here you can think of it as, I'll call it L, because L will be for linear spaces. He suggested that if Ij is an edge, this is a non-edge, right? Not in here, you still put a 0. If it's an edge here, you put a variable xij. Just a separate variable for every edge. And then you look at this matrix, and the observation was that this condition continues. This is if and only if, so the there is no perfect matching if and only if the determinant of this matrix L P of X is not identical. So first we have to realize that this determinant is now a polynomial, it's not a constant, right? It's a polynomial, and the claim is that if this polynomial is identically zero, then there is no perfect matching. That's obvious. Sorry, that's not, well, anyway, if and only if. So let's talk about this. This also captures the perfect matching problem. And the only thing which can go wrong, well, you know that in the formula for the determinant, which I might as well write. The matrix is the same sum of the permutation, but we have -1 to the sign of the permutation. So the only difference between permanent and determinant is the sign. Because of this sign, you might think that there will be cancellations. You know, the polynomial can be zero despite the fact that you know, there is a perfect matching, maybe two perfect matching will cancel each other. But of course, this cannot happen because all the variables are distinct. Every monomial contains a different set of variables. So that's easy. But then the leap was in asking this question. He said, okay, this problem for this individual variables, it's in P. So this determining whether this kind of determinants are identically zero is in P because it's equivalent to perfect matching. This is suppose instead of these variables, we just have arbitrary linear forms in some set of variables. Sorry. So that's maybe a channel matrix. So what he asked was whether the determinant of L as a polynomial is identically zero. The question is whether this is in P. I give you such a linear space. What is this? This is just a linear space of matrices. Right, parameterized by.
I missed something. How'd you go from LG of X to this one?
I didn't go. That's a leap. He said this is a very special case of this.
Sorry, what is this one?
This is you put an arbitrary. So that's an linear. I should have said linear form. Thanks.
Spaced for a second.
That's okay. A linear form in variables X. So you put an arbitrary linear form.
Did we lose the graph now?
No, there's no graph. There's nothing. It's just
That's the matrix.
So let me say you can in order to present it to an algorithm, how do you present the linear space? One natural way is to pick a basis for the space. So that it will often denote some basis A1. You might as well assume that M is actually the dimension of the space, and so given M matrices, and now I should say that we are working over some field. I said earlier that we are working over some field, and in the lots of the questions I asked are interesting for every field. Some of the results are states are hold for characteristic zero fields, algebraically closed or large enough. Most of them will hold for just large enough fields. Some hold for all fields. But anyway, the interest is in any field, so we fix the field, and that's where we work on. Okay, and this is the question. So I should say, by the way, that P was really defined by Maass. It was defined in the 60s by several people. He was one of the pioneers who defined, what he called good algorithms or efficient algorithms, so polynomial time, deterministic algorithm. And this is the question I'm most interested in. We don't know the answer to this, whether it's in P. We'll soon tell you more what we know about it, but we don't know. And I wish you'd help me.
I think when you write generated by A1 up to AM, it means that L of X is like X1 A1 plus X.
Yeah, exactly. Yeah. So I should even write it explicitly. This means that L space is the sum of AI. Set of variables. Exactly. Just a linear space just happens to be a linear space of matrices. Okay. Yeah, so we don't know the answer to this.
Can I ask you a question over Zoom? Is that possible?
Of course. Yeah, well, I can hear you, yes.
Sorry, I've never done this before. So for the permanent to be zero, there's the Frobenius-Koenig theorem, which says that the permanent is zero of a 0-1 matrix if and only if there is a submatrix of all zeros of certain dimension, right? And it seems to me there's a completely analogous theorem for the question you just asked. And I'm wondering whether the problem with that theorem is that it's not in P to check it, because
yeah, that's the problem. And we'll get to, when we get to invariant theory and non-commutative algebra, we'll talk about this. But let's wait for that. Yeah, anyway, it's not in P to test this. And anyway, it's open. If you find any way through this or any other theorem you know to get an algorithm for this problem, I'll be very happy and the whole community will be ecstatic.
Okay. But you are aware of this result of Panov, which I'm talking about?
Yeah. But I think I'm aware of several results like that. I'll state.
Okay.
Okay, good. So this is a problem we are interested in, and now I want to tell you some of what other places where it came from and why it is interesting. But we might as well call. So L is a singular space. Only if this holds, the determinant is identically zero. Now let me say that you can define it in another way. You can say it's a linear space containing only singular matrices. The two definitions are the same if the field is large enough. So let's assume the field is large enough, and then it's the same. The determinant formally of this polynomial is identically zero, or every matrix in this space is singular. Okay. By the way, this I'll tell you about some motivations. I will not tell you about other motivations which I don't quite understand. Like in algebraic geometry, in a famous paper, Eisenbad and Harris, they say that understanding these spaces, singular spaces, is the same as understanding torsion-free sheaves over projective spaces. I don't know what it means, but there are other reasons to study this that I don't understand.
Say singular space of singular matrices.
Yeah, space of.
It's not anything about like singular points on this map.
No, absolutely not. Just it's a name. It's a name. It's exactly all matrices are singular equivalently. The formal determinant here is identically zero. Okay. So I want to talk now about algebraic complexity theory from several points of view about polynomials. Maybe just make a comment here.
And Avi, can I ask another clarification?
Yeah.
What does it mean to be in P with respect? What is the input?
Yeah, it's a very good question. It's a very good question because I talked about arbitrary fields. So if you're talking about a finite field, you're getting these, in any case, you're getting these matrices, right? So if it's a finite field, I just give you these matrices of constants, there is no problem. It's true that over, infinite fields, so all sorts of fields, what is the input length, what is the, so the most natural way of saying what P is for every field is that you want a polynomial number of operations or field operations, and field operations are just constant size. Adding, multiplying in the field is the constant size, and description of a field element is a constant space. Anyway, yeah, that's one can get into this if there's anything that looks like an algorithm that has a polynomial number of operations, field operations. We'll worry about this. But anyway, it's a very good comment. Thanks. I want to just make a comment here that an extension of this question is to put some polynomials here. Another nice one question. Of course, you want these polynomials to have some nice description. And if they have a nice description, they are given by a formula, or they are themselves the determinant or something like this, then you know, this sort of reduces to the linear case. Via something called the Higman trick. So, you know, it's a clever trick and it's related to something else I'll say, but I'm just for, you know, this may come up or you may ask, think about it. It's not, might as well study linear space, basic message. Okay, so now we want to talk about algebraic complexity theory, about polynomials. So we again now, you know, we just think about this polynomial ring. And here's a very basic and well-known fact that was discovered all over the place by lots of people. In computer science, it is usually attributed to DeMillo, Lipton, Schwartz, Zipkel from the 70s. But, you know, mathematicians discovered this long before in various forms. I mean, the basic message here, this theorem would be that if a variety, algebraic variety is not the whole space, then its measure is zero. So that's a quantitative version of this. Suppose you have some polynomial here of degree d. And we want to test whether it's identically zero. So one natural way to test whether it's identically zero is to plug random values to the entries and see whether it's identically zero. In fact, we could have done, that's a particular case, that's this question. This is a special case, of course. Maybe this question have a name for it. It's a SDIT, it's a symbolic matrix. A linear space can be thought of as a symbolic matrix identity testing. So now I'm looking at polynomial identity testing. So PIT given F. We will talk about given F in a second, but the theorem, so this is a generalization of that. I mean, it's, for any polynomial, not necessarily the determinant. Suppose that in your field you have some set S, any set. And think about choosing random values to the variables from this set. Then the probability that f of over randomly picks in S. I assume that F is not identically zero. It's most. Now, so again, you pick random values. If S is large enough, bigger than the degree, you will catch it. You will have a proof that it's a non-zero. Right. You've seen it. You know, a very special case of it is the fundamental theorem of algebra. If it was a univariate polynomial, then it can have at most d root. So if you take a set bigger than that. And the extension is proved from this base case by induction, which is simple, if you haven't seen. Okay, good. So how, I mean, but to do this, to test whether, an evaluation is zero, you need to evaluate it. So therefore, you have to have a way to evaluate it, either a black box or it is given by something that you can compute. So we will generally assume that F is given
Field is finite?
Sorry,
The field is finite?
any field, I mean, whatever field. Yeah, so I'm going, f is given by, as we said, I mean, okay, so let me, given by a circuit or a formula, which is arithmetic. So what do I mean by arithmetic formula? For polynomial, it just has, plus and time and constants from the field. Thus, basically it looks like, plus 1, 7. Plus can have, you can put coefficients from the field here, and not just add, but take linear combinations and so on. And the difference between a circuit and a formula is that a formula is a tree, it's an expression you can write with parentheses. Circuits can have things like this. It turns out it's a magical property. I don't want to get too much into algebraic complexity theory. I will get to some, but that circuits and formulas are roughly the same power. They're quasi-polynomially related in power. Circuits are more powerful, but not much more powerful than formulas. So most of the time I'll work with formulas. This is something that's not true in the Boolean case, so we don't believe it's true. Okay, so by the way, what is does determinant have a small formula, small circuit? What do you think? I mean, the obvious way to write down the determinant is n factorial terms. Anybody knows a small arithmetic circuit or formula for the determinant? What's the complexity of the determinant? I mean, you should know. Even people who know can answer.
Formula or circuit? Quasi.
Yeah. Doesn't matter. Polynomial is quite small. Yeah, much smaller than n factorial.
Quasi.
Yeah, of course. Yeah. So you know this. How do you compute determinant when you need to?
Matrix multiplication.
Well, I don't know. How do you compute determinant with matrix multiplication?
Oh.
I'll give you a matrix you want to compute the determinant.
You get it to triangular form and then take the
How do you get it to triangular form?
Gaussian elimination.
Yeah. What do you need for Gaussian elimination?
A computer.
No. What operation? What operation to use Gaussian elimination?
Matrix multiplication.
Well, you add and you multiply and you divide.
Yeah.
But I didn't allow you division. It's a polynomial. Why should you divide? Okay, so you've never seen this, obviously, and I know some who have seen. So the determinant n has just plus and time. So there are various ways to see it. I'm not going to go there. I'll just tell you. First of all, it's a general fact proved by a variant that if you have any polynomial computed by arithmetic circuit with division, so polynomial, but you are using division like Gaussian elimination, you can always eliminate the division with an extra factor of n. And another way is a very simple and explicit algorithm that I could describe, but not now. So there is a way to do it without division. You have to remember this. So it's an easy problem. And we are going to talk now about hard and easy problems. So questions? But yeah, let me just, one point I want to make about this PIT problem is that what we see is the PIT and in particular this SDIT problems have a fast probabilistic algorithm, right? So we see that by this simple theorem that PIT, SDIT are in randomized polynomial time. It's a one-sided error kind of thing. If you want PPP, you can write PPP. Anyway, so it's there's a fast probabilistic algorithm. So the question of whether it is a deterministic polynomial time algorithm is a de-randomization question. And that's definitely one of my major attractions. We'd like to, I mean, the general task of de-randomization is to take probabilistic algorithms and remove the randomness, make them deterministic. And I invested lots of time on this project. So, okay. The other connection to algebraic complexity is, and for this is result is related, is you know, what is for general polynomial. So algebraic complexity theory.
Avi?
Yeah.
Just a question. When you talk about the size, so a circuit means that you have the tree of addition and multiplication.
Yes, a tree, or actually it's not a tree, it's just
A graph of.
a graph, yeah, directed graph, yeah.
And the size would be the number of layers?
No, the number of gates, the number of operations. The number of operations. So size is the number of field operations. Okay? Yeah, thanks. Yeah, no, there may be things that are yeah, so this seminar became to my great delight even more diverse than you. What is the complexity, circuit size, formula size of natural or such so again, X is the vector of variables, multivariate polynomial. And the most important name associated to this is variant. In the 70s, in the late 70s, he developed a complexity theory analogous to the Boolean complexity theory. In particular, like we have P and NP, P would be the easy problems and NP would be the natural, let's say, search problems or natural decision problems. He wanted to define analog, so they are called VP, not by him. VNP. Okay, so these are the easy to compute. So with the poly size. I like to be ambiguous, even though they are not quite the same up to polynomials. But anyway, these are easy. We will, the game we'll play is between polynomials and exponential, so we wouldn't care about some small method. And these are natural, not search problems, but counting problems. Counting. I'm not going to define this, but you have already seen the permanent polynomial. When you compute it, evaluate it on a matrix like this, 0, 1 matrix, it counts the number of perfect matches. So it's very natural associated to counting. And I don't need to define it because I'll define it through a complete problem. So both of these guys have complete problems. So which variant proves? Determinant is complete. So, VP and so just like you know that you can define NP as just everything reducible to satisfiability of a Hamiltonian cycle, and P is everything reducible with appropriate reductions to linear programming set. It's the same for algebraic complexity, and it's even a cleaner theory than the Boolean case. I mean, in general, the algebraic setting is cleaner in the sense that you have more structure, more is known than the algebraic domain. And I actually, okay, how many people have seen this theorem? Just wonder, it's good. Yeah, don't be shy, it's okay to know things. Okay, so given that, let me, because it's short, I'll prove this. Okay, this is one of the most complicated reductions that we have a few complicated reductions in complexity theory. That's one of the more complicated ones. So I'll not prove this, but we'll talk about this in a second. So what do I mean by complete? So you need a notion of reduction, and that's a really cool thing that makes this theory so nice. Here's a notion of reduction between two polynomials. You say that f, let's say, k is reducible to. So less than or equal is reducible to. Easier than, like, if you could compute this and you could compute this with a little effort. The g of if there exists, let me write here, fine, even though I mainly look at linear, find linear functions, j, such that, what do you want? You want to compute this. I give you a machine that computes this. So you want to use it to compute f. And so you just plug here for the z's linear functions of the variable y, right? Such that f of y is the same as g as L1 of y. You see, that's a very natural definition. It's just about linear projection. And it also will fit perfectly with the linear spaces. I mean, this will generate for us, such reductions will generate for us linear spaces. So let's see some of these questions about just this definition. Yeah.
Here, do you allow division or not?
No, I don't allow division at all throughout. I mean, maybe towards the end I'll mention. But as I said, for this setting, what I'm talking about here, it doesn't matter whether you have, if you have division, you can eliminate them and be irreversible without division. It will become interesting at the end of the talk if I get there. Okay, so let me prove this first theorem. The determinants complete. VP is a class for now of everything that has polynomial size formulas. So the statement, if f has a formula, has the formula and the size as formula, then it is reducible in this sense to determinant 2s by 2s. If you didn't see this, that's such a beauty. So it's very natural. I mean, you do what you have to do. I mean, what do you do with formulas? You induct on the structure, right? I mean, for variable, if you just have a variable xi, you can build a little one-by-one matrix and put xi in it, and the determinant of this matrix is what you want. So in general, we want to build for formula F, we want to build for its MF, such that determinant of MF identical, right? So this is easy, and suppose now that F is G times H. What do you do? Good. So if we have MG here, let's say MH here. We define this to be M sub F, we got what we want. Very good. Now what about
That's just one entry of the.
what? Not clear what to do. It's not clear what to do, and as often happens, I mean, one can think of several ways to get around this. I'll tell you variant way, well, I don't know if too many. I mentioned Higman's trick in the beginning. It's in some sense achieves the same purpose as this. But anyway, I'll tell you variant trick. So as often when you have an induction and it doesn't work, you need to strengthen the assumption and then appropriately, and then it works. So we will insist that any matrix M sub F we have, just keep it throughout the induction process. It will have a subdiagonal of ones and zeros below. And once we do this, these things will work. So let's see why they work. Well, I guess the first thing, maybe we need to make it 2 by 2, right? I mean, I don't know. How would I do it? 1, 0, 1. Maybe something like this. Yeah, this 2 by 2 matrix, the determinant is x1, xi. So for 2 by, and you have 1 below the diagonal. Okay, what do we do? Actually, please. Yeah. So suppose now we have to revisit the multiplication, right? So let's revisit it. Suppose I have here ones on the diagonal. And 0, 0, suppose I had it, but it's true that the product is fine, but this doesn't have ones below the diagonal. So what can I do? Yeah, put the 1 there. It doesn't hurt anything. Okay, good. So that was fine. That was it. Okay, so how do you do addition? You do addition in the same way. Now you can do this thing. Let me explain how. This is GNMH. You want to add the determinants. So here's, let me tell you the answer. So think of this. Let's add 1 row and 1 column. We put 1 here, 1 here, and 1 here, 1 here. I think. So what's the point? I mean, the point you will think about expanding the determinant. I mean, if you take, for example, this guy, I mean, you can take either this guy or this guy, right? If you take this guy, you really have to take this one and this one and this one, this one, and this one, and you get 1, forget signs. And so you get the determinant of MH. Like this one, then you have to take this and this and this, and then you take it. So, what's wrong?
You have a missing 1 in the diagonal.
Yeah. And I have a non-zero here, which I should have 0. What's the solution? Exchange these two words. All right. Yeah. Very beautiful, John. So now let me move to the third question. The permanent.
What's the Higman trick?
What? I will not tell you now. I promise I can tell you. It's a way to get a polynomial into a linear function. I mean, you get a matrix of polynomials, you get a bigger matrix of linear forms that computes the same determinant. And in some sense, you can think of it. So maybe it's simpler. I don't know. Anyway, I really love it. So now about the permanent.
So it's just a theorem. It's a theorem that states that you have a formula, you have a polynomial, then it reduces in polynomial to the linear case.
In the, you mean the matrix?
Yeah.
Yeah, but let's talk about it. At the end. So I just want to stress what you're seeing here in particular is that a corollary of this theorem. A corollary of this theorem is that PIT is reducible to SPI. Already in the normal sense of reduction. I mean, if you have an algorithm for determinant with a symbolic identity of determinant, you can do it for any polynomial given by a formula, by this reduction, because it's complete. It's another place where we've generated linear spaces and asked about their singularity. So now about the permanent. I said that it's complete for VNP. So what does it mean? It means that it can. Well, let me. I'm not telling you what is a family of polynomials that are reducible to it. So I will not cheat a bit. I'm not going to define it. But let's just compare it to determinant, which is complete for P. So we can ask the following question. Let's define K of n to be the smallest K that and my matrices is reducible to the determinant K by K matrices. So basically, the VP versus the VNP question is whether this K of n can be polynomial in N or not. Which will be the analog of the P equivalent P. I mean, seriously, it will be an analog. I am not going to give a law, I mean, it's a separate lecture to talk about VNP and the class of problems in statistical mechanics and in algebraic combinatorics that it captures. It's, you know, there are many, many polynomials that people are interested in for a variety of reasons. They are all reducible easily to permanent under this, you know, this notion of reduction. So we really care about the permanent. And yeah, and to understand the VP versus VNP, it's sufficient to know this K. Now, if you think about it, you can start playing with it. And in fact, Polya, many, many years ago, noticed that the permanent of a 2x2 matrix is the determinant of another 2x2 matrix, or even after this, let's say minus. Is a linear reduction, which is very simple. And you also notice that for 3x3 it doesn't work. I mean, it proves that there is no such reduction for 3x3. From the completeness of determinant, I claim that, so it's easy. It's not clear that K of n is finite a priori, but because of the completeness of determinant and because the permanent has formulas, I mean, not small, but exponential size, we know that so this is K of 2 and K of 3 known to be bigger than 3. That's my polynomial. Curve n is at most exponential in n. I mean, the most obvious formula for permanent is n factorial, but let me give it as an exercise. It's a nice exercise to find formulas for the permanent that are just exponential. Anyway, so we know exponential, we want polynomial, we don't know the bound. The best lower bound known is due to Young from about 10 years ago, I think. Yeah, early 2000. Quadratic lower, maybe. Now, this is a beautiful proof. A simple algebraic takes 10 minutes to describe. I will not do it. But let me say that in a sense, it is the trivial lower bound because the number of variables is n squared. I mean, it's not obvious. I mean, the fact that the number of variables is, I mean, the matrix n by n. It's not obvious. I'm just saying that I mean, what we need to beat really to get anything really interesting is beating n squared if you process. Okay. Let me mention that this question, the algebraic question of separating permanent versus determinant, or VP versus VNP, you know, one of the attacks mounted on it was the so-called GCT, geometric complexity theory. This GCT by Montgomery. Around 2000. And it's an attempt to separate them through representation theoretic and algebraic geometric techniques. I'm not going to describe it at all, but what I want to say at the end about invariant theory and this other approach is related. It turns out that two approaches meet, and there's a really beautiful connections that actually also talk about linear spaces, but I will not have time to discuss. But anyway, it's a major question. It's the analog of our major question P versus NP in the algebraic set. So now let me tell you about the really shocking motivation for understanding the symbolic determinant. Until now we understand, I mean, I should have said this result of the completeness of the determinant is what explains why the determinant is the most important polynomial in mathematics. I mean, this is why you see it all over the place. If you think about it, anything you had, any algebraic identity you had, you could express it like that. Sometimes it's natural to express it like that. So potentially, all of them are like that.
Is there another polynomial or something else that you can define easily that would serve the same?
I don't know something like that. Of course, we know it's also it captures linear algebra, right? It captures systems of equations, solutions to linear system of equations. But this, as opposed to the way it captures solutions to linear systems, which is more or less by definition, this is not obvious. That it captures all the algebraic identities. So now I want to tell you about lower bounds, connection to lower bounds. And this is the work of Maass. So. 2001. Yeah, I don't know if everything I said so far, makes you drop everything you've done so far and just try to understand linear spaces and the complexity of their symbolic determinants. So they have two results in their paper. One is a de-randomization results, a conditional de-randomization results. This is something that we are extremely familiar with in the Boolean complexity, and they did one for algebraic complexity. So, I mean, the general philosophy of conditional de-randomization results is this connection between hardness and randomness. If you have a hard function, you can use it to remove randomness from computation. That's the general philosophy that we've understood for a couple of decades now. And they show that in the algebraic setting, it works as well. They prove that if Kerfan, so this is complexity of reducing to, I mean, permanent to determinant. So suppose permanent is much harder, it's exponentially harder. Suppose that this is really requires. This means this implies that it's PIT and therefore also PIT. So we have a probabilistic algorithm for PIT and symbolic determinant. You can de-randomize it if the permanent is very hard. Okay, so it's analogous to results in Boolean complexity theory. And in fact, it uses the main tool there, which is a pseudo-random generator that Noam Nissan and I developed, but does it in the context of algebraic complexity, which needs additional ideas and tools. Anyway, so that's not the shocking thing, that's sort of, but this connection between hardness and randomness, they reverse it. Here's the shocking result. Can separate. In fact, you can exponentially separate it, VP and VMP. Now, I put it in quotes. So what does this mean? It means that there is an alternative, which from the point of view of any complexity theorist is just as good. Either you prove this lower bound, so permanent is much harder than determinant, or you prove another lower bound. Oh. Not. This is just, you get some, unknown and long sought after lower bounds in Boolean complexity. So it turns out that they only derive an alternative, but anyway, de-randomization implies hardness. And I think that what's so shocking is that if you haven't seen a result of this nature ever, then it's really, we look at it and it says, if you give me an algorithm to some problem, this very problem, but anyway, you give me an algorithm to a problem, you immediately get another problem is extremely difficult. It's a consequence that doesn't, no, its logic sounds really weird. Anyway, this is that's the real reason for me to, spend time on this problem. It will give lower bounds, which is so okay, good. So what are we doing with time? So first of all, questions about that. I'm not going to prove it, even though I could. I mean, it would take me maybe an hour or maybe even less, but it requires some understanding of tools from complexity theory. In the main non-trivial one, which is used, which is also not big deal, is a non-deterministic time hierarchy, and some, well, maybe some interactive proofs. Anyway, these are tools that are available. The proof is not long once you know by now what's considered very basic things in complexity theory. You have to think about how to do it, but yeah, it can be explained in an hour. Questions?
Maybe just throw a subpoena to how can it be that, like, so if you solve this problem somehow, it makes some gadget in the reduction word.
The peanut was in the word non-deterministic hierarchy. So it turns out that if you had a circuit, if a small circuit for permanent existed, then you could guess it. But if you could guess it, what does it help you? You can guess whatever. How do you know that it's correct? Then you use the self-reducibility of the permanent, I mean the throw expansion kind of thing. And you can verify it if you had a symbolic identity testing. You could verify that the circuit is doing what it should in the reduction, to smaller and smaller sizes, which is by. And then you would have, then if you assume this doesn't hold, you get some extra things which allow you to collapse non-deterministic exponential time to NP, basically. And this is known not to be true. So anyway, that's let me know.
I just wanted to make a comment that like this type of result, if you know that like class A and C are different, like P and X, and you put something in the middle, then
Yeah, but so this is much more sophisticated, but that's a very good comment. If we know that if we proved that P equals to NP, then that's an algorithm, right? We have given an algorithm to satisfiability. We immediately prove that NP is different than let's say exponential time. Right? Because we know that whenever we have two, so X is contained in Y, it's contained in Z, and we know that these guys are different, then once we put this equal here, which is the algorithm, we put a lower bound. But yeah, this is much more sophisticated, but a very good point. Okay, so maybe we'll take more questions. So let's take like 5-minute break and continue.
דרך גם מבלבל אותי קצת מה שכתבתי באימייל. אני לא אמור לקבל מזה. כל דבר עם שם בכל כאילו.
כן, נכון, הייתי צריך להעיר את זה, אני אעיר את זה.
לא, אולי אבל אפשר.
אז זה בעצם כל כאילו. זה גרסת פקטור. ההבטחה הרגיעה של הטרנספליט, שאתה עושה, אבל כרגע יש סיבה כלשהי לחשוב שיהיה הטיה לכיוון. אתה הוספת הטיה לכיוון. אבל זה לגמרי בעקבות הוספתם או רנדום סיינס. לא, משהו ברגע של הרנדום סיינס הוספת את ברגע של רנדום סיינס הוספת אני קוראים דבר כזה, אז סיינס, אבל הוספת
let me make two comments because before I leave, I will not leave algebra completely. But anyway, one comment that I forgot to mention, it's even if you put it in NP, you get the same consequence. So even if there is a way to certify that all matrices in your space are singular, okay, you don't need an algorithm. This will be enough. We don't understand it to this level, right? That's one comment. Another comment is about, as I said, well, PIT, basically the same problem. One approach to this problem of, PIT, of getting polynomial time algorithms, is a very natural sort of program, which is just, let's prove it not for general formulas or general circuits, but for special cases. And there's been some success along this way. I'll mention just two. If the polynomial f, so I want to, so special cases. We'll see more as we go along special cases because trying to understand the variety of special cases, maybe will get us techniques to do the general thing, and somehow techniques seem to be all over the place for different special cases. It's not clear what to learn from this, but one is when f is of the following form, it's what's called formula. Namely, it's a plus of a constant number of gates, and here you have multiplication gates. Another linear. So there are three layers. Here are the variables. There's three-layer formula, which has a plus and times a plus, right? So it's the sum of products of linear forms. And I give you such a thing, you want to know whether it's identically zero. Let me just comment that if this number, let's say k, if k is 2, you know how to do it. This is whether one product of linear forms equal another product of linear forms. You have unique factorization and but if I give you 3, it's really the problem of whether so 3 here. It's whether A plus B C identically, where each of these is just a product of linear form. This is already highly non-trivial, and the way it is done is by techniques from combinatorial geometry, as it happens. This is mainly just trivial filter. Another one, it's one special case. Another special case is you saw those who were in the talk yesterday. F is a read once branch algebraic branching program. I don't define this model, but because many we have not seen anyway, it's a very general thing and well, quite general. And doing it deterministically was important for concerns having to do with the GCT, geometric complexity, and with invariant theory, but I will not get it. So this is what's done by normally and Forbes and Ship. Okay, now I want to talk about tensors. Tensors and tensor ranks. So there'll be lots of ranks. I mean, I know I didn't mention rank until now, but now I mentioned lots of ranks, so I have to be careful. So tensors generalize matrices. Matrices are two-dimensional tensors, and then well, I gave a talk. Those who want introductory talk to tensor rank in May or June. Here it's on the web if you want to watch it. And I'll just consider three tensors for now. I mean, you can consider tensors of any dimension. It's just easiest to think about, which is beyond matrices. Matrix rank is easy to compute. So now we want to talk about things that are hard. So tensor rank. So you can think of a tensor T as simply a map from, you know, if it's an A by B by C tensor, then it's just a function. The entries of this box. That's a tensor, and the tensor rank, tensor T, the smallest, let's say R, if T equals T1 plus T2, TR, and each one of them is the rank, tensor rank 1. So each one of the TIs, maybe I should have written it like this, same notation. What is the rank 1 tensor? It's just the outer product of three vectors, right? Like a rank 1 matrix is the outer product. This is a very complex thing to understand. Yeah, anyway, so I have this survey thought. If in the case that, let's say, A equals B equals C, and T random, then you expect, or most tensors have high rank. High rank is quadratic. Then. So most tensors have quadratic rank. And I want to tell you about a really stupid law for tensor rank. It's a stupid, I should put in quotes because it's the only thing we know how to do. It's, well, not the only thing, but it's one of the major things that we know how to do. We only know how to get linear law bounds in terms of A. Linear 2, 3, on special ones, and they go by various flattening ranks. So let me tell you what a flattening rank is. But before that, I mean, it will be very natural if we think of linear spaces, because what is a linear space if not a tensor? If you look at this, oh, it's not there. What's a linear space? If we have then this is, I can just draw it. I mean, I can draw it any way I like, but I can draw A1 here. Here. No, you can think of the input to this symbolic determinant as a tensor. And M, I think we made this notation of the dimension of L. This number M, so we assume they are linearly independent, otherwise we would remove one. So it's a tensor. Free tensor. And we could, I mean, it's clear that M is a lower bound to the rank of this tensor. I mean, it's what does it do? So let me, there was a flattening rank, so flattening rank. Let's say of an A by B by C tensor, tensor T, let's say in direction, in this case, in direction A, is simply the rank of this tensor when you flatten out the B and C parts. And you write it as a matrix. And you can similarly look at the rank, and the rank here is really a low bound. I mean, any regular tensor will give a rank of a matrix in any decomposition you do, and you can do a similar one with see, and the flattening rank of a tensor is just a maximum of this. So this is a low bound, so the maximum of this, and this is a tensor. But obviously it's a bad low bound because it's, you know, it's the most linear, right? And it's, I mean, if they're all equal, this ABC is just linear, so it's stupid. So here comes a twist to the story, and that's mainly the work of Valiant. So it's not really, you cannot get a lot from this for tensoring, but here's a twist by Valiant that's absolutely important for understanding the complexity of matrix multiplication, but it's actually extremely important for lots of other reasons. And this is a theory of asymptotic rank. 70s and some in the 80s. I wrote a series of papers on the asymptotic spectrum of tensors. Jeroen Zwiedam and he was a postdoc here, I guess left a year ago, are writing a sort of modern survey of these works, of this big theory that should be available, I promise, or that you will be volunteered to read it imminently, like a month ago, but it's still not quite ready. Anyway, so that's asymptotic. One can say of, in general, of ordered semirings. Tensors are naturally a semiring because you can put a tensor, I mean, it's a three-dimensional thing, but you can maybe think of a matrix. One. So this would be an addition of two tensors and tensor rank of two tensors. So there are plus and type operations associated to tensors which define the semiring, and you can order it by linear projections. So you can say that T1 is less than T2, just like Valiant says that T1 is less than T2. You could embed, after linear transformations, you can embed this tensor in this tensor. After all, the tensor is a polynomial, it's a multivariate polynomial, a multilinear polynomial. You only have to remember that you want to keep it a multilinear thing. So you allow only linear transformations with respect to its side, you know, one on every direction of the tensor. So that's an order semiring, a particular order semiring is a theory works for arbitrary semirings and found applications recently. But what it aims to do first of all, the theory aims to understand a notion that relaxes the tensor rank, which is asymptotic tensor rank. So let me define this. So it is asymptotic tensor rank. You want to understand tensor rank in an asymptotic sense, which is to say in an amortized sense. How does it behave under tensor powers? So the asymptotic tensor rank of a tensor T is the limit, as let's say k goes to infinity, of the tensor rank of T. If it's k tensor power, and then of course you normalize this by. Okay, so in matrices, if you did this for matrices, it's well known that tensor rank of matrices is a product of the ranks, right? So in matrices, it's not interesting. The asymptotic rank and the normal rank is the same. For tensors, it's not the case. It can be smaller. The asymptotic rank can be smaller. There are many reasons to be interested in this, but the primary reason is matrix multiplication. So first of all, matrix multiplication is a tensor. The problem of computing matrix multiplication is basically the question about what's the tensor rank of the matrix multiplication tensor. To see that it's a tensor, if you want to think of two matrices, the product of two matrices, AB equals C, you want to compute this, that's a bilinear question, but you can equally look at the trace. I mean, it's the same question, really. To compute the trace of this matrix, which is a trilinear form, which is basically a tensor. I mean, that's basically this tensor, maybe I should say, the tensor of matrix multiplication is simply, first of all, it's an n square. If these are n by n, these matrices, let's say, then this tensor is n squared by n squared by n squared, in which you have in positions ij, jk, k, you have 1, and in others, it's a very concrete tensor. But the amazing thing, it's not difficult to prove, is that if you want to know the matrix multiplication exponent, right, whether it's, we know that somewhere between, maybe omega is the matrix multiplication exponent. Basically, the complexity of multiplying matrices is the same as saying that the tensor rank of this matrix multiplication tensor to the omega somewhere between 2 and 3, and we know that it's closer to 2. Then here's the amazing thing, which is simple. The asymptotic tensor rank of this matrix multiplication tensor is the same. Tensor rank. So here you don't save, and the reason you don't save is because matrix multiplication has a recursive structure. If you can, I mean, you have an algorithm for some size, you can use algorithms for bigger size, but recursing. So we should be interested in that. And there's another, I don't think I can call it a conjecture, but it's sort of amazing. So if you want to understand matrix multiplication, should be interested in this possibility. This possibility says the following: that a asymptotic tensor rank of any tensor is roughly the same as the flattening rank. But at the end, asymptotically, it all drops down to basically the size of the. We have no idea whether it's true or whether there are any counterexamples. I encourage you to think about it. This is a stunning possibility. If it's true, then the matrix multiplication exponent is 2 in particular. That would be one of the.
What's the motivation for
That we don't know.
for this projection?
But that we don't know that it's not true.
No, yeah, of course, but why do you think it should be true?
I don't think it's really true. I said it's not quite a conjecture. I think that bold statements sometimes, get people to try to refute them. So it's very nice if somebody finds a counterexample to this. Okay, so anyway, this reason got started to define the asymptotic spectrum. I'm not going to define what's the asymptotic spectrum of a ring here, but in particular, one result that he proved in the case of matrix multiplication. So asymptotic matrix multiplication is a very simple situation where we know that it's a set somewhere between 4 is just a real line here. It's not hard to see that it's a set in the real line. I'm not defining it, but anyway, it's a set in the real line between 4 and 2 to the omega. If omega is 2, then it's just 1 point. And what Strassen proved, this is sometimes called the X of this. So this is really a subring generated just by the matrix multiplication tensor. We prove this. It's connected. So it's actually the full interval. In general, understanding the spectrum helps understand. Basically, it's about generating inequalities. You will eventually want an inequality on the tensor rank, which is relating your tensor to some identity tensor, but you get it from other inequalities. That's how the whole field has progressed. All you know works by generating inequalities, and having this information helps in using non-monotone inequalities. But anyway, let me not go into this. What I want to say is that this theorem uses something very, I think beautiful, and I was going to show you the proof, but that's clearly I will not do. So I'm going to show the proofs of several linear algebra things, but I'll just state some part of, so inside this, it's a, I don't know if to call it a lemma, because it's also a theorem. It's not clear why it's even related, but it's a theorem about linear spaces. It says that if you have then there exists linear transformations on the left of the right of this tuple of matrices with the property that, so we apply, so let's call this so that giving us L prime, which is B. See, so it's another matrix space. And this matrix space we have the following structure. Sorry, and M, let's say the most n squared over 4. It's not there, it's somewhat bounded from the first space. You can get any, put any constant. It's just nice for the picture, and I can divide it to half. Maybe L, so this is I don't know, L1, L2, sorry, 4. So after this change of basis, you basically, this part depends on the other part. Somehow you put all the linear independence in this corner. So L1 is in the span. I think of it as just linear forms, like in Edmonds. These are linear forms in the variable. So we have a linear form in every entry in the span of it's not clear why it's interesting for this, because we don't know what the connectivity is about, and actually the reduction is quite sophisticated. But one way to think about this result is, or one consequence of it, is that suppose you have you have an algorithm that computes matrix multiplication, but some adversary comes and massages the result in an arbitrary way by adding to it some linear forms in all sorts of, in the various entries of the result. And all you know is that the dimension is not too large. Then because of this, you can compute, you can still use your algorithm to compute matrix multiplication without error on, let's say, n over 2 size matrices. It's a consequence. I will not go into this, but anyway, it has meaning as error correction or average case to worst case reduction in this framework. So I will not show you this. We have a simpler proof than it's nice, but I realized already in the previous hour that I will not have time to show the proofs of the theorems I wanted, so I'll just take them, I think. And just lots of results are known about linear spaces, and many of them started with quite complex, sometimes using information from algebraic geometry about space. I'll soon tell you another type of result, and then many were simplified and some were not simplified using cool linear algebraic techniques. Anyway, that's another place where linear space is shown. I want to show you where they show up in graph theory. Questions about this? I have two more topics, this graph theory and this non-commutative algebra, that kind of thing. So we already saw that determinant, linear spaces capture matching. So matching is a graph theory problem. That's one. I was going to explain how linear matrix spaces arise in the study of K connectivity of graphs. It's a paper I have. So I ran into linear spaces in lots of places where I didn't plan to. This is a paper with linear lovers from about 86, in which you have a characterization. So I will not write anything down. We characterize the K vertex connectivity, namely that between any K vertices of a graph, you have the K vertices, joint paths between them. We characterize it using a physical model where you put, like think of every edge as a rubber band and give it some elasticity or strength. And then you compute something with it, some determinant, basically. And then, if your graph is is K-connected or not. And it also leads to better algorithms in some parameters of K-lot. But let me not talk about this. I want to, at least here there are no open questions I want to ask you, but in the other physical model of a graph theoretic problem I want to talk about is the structural rigidity problem. And both of them, they are embeddings into of vertices into space. So let me talk about structural rigidity, which is a very natural question about embedding graphs into space. So we have VS graph, and we want to know whether it can sit in space in a way that will not move. So what does it mean? So we say that it is infinitesimal. In RD, if you can map the of the vertices RD such that the vertex locations of the field changes the distances. I'll give an example in a second, so we will see what I mean. But I mean, of course, this cannot be true because any rigid motions, you know, you can just move any configuration of points in space rigidly by translation or by rotation, and all the distances between them will be preserved. So you say except rigid motions. So let's do some. So it depends what the dimension is, and things change with the dimension. So let me give you some examples. Equal to. This is rigid. Triangle, the graph of triangle is rigid. In fact, any embedding of the triangle is rigid. But if you have something like this, a full cycle is not rigid, right? You can push this in and push this out. And this guy can have. I want to explain why the infinitesimally, why didn't I let you move it in general? There's a different notion of global rigidity, which is no change of the vertex places. This is also rigid in the sense I defined, but if you allowed global motion, you could flip this triangle, right? You could make it look like this, something like this. But that's not perturbation. Anyway, so that's and of course this very graph, if I consider the R3, would not be rigid, right? In R3 I could flex it. Okay, so that's structural rigidity. And why am I talking about it here? Because it also has a representation in the sense of matrix spaces, in our spaces of matrices. And I will not prove it, but it's really easy. I mean, you basically want to write the equations of the direction in which you perturb, in which you move the and then you want to measure the distances, or basically subtract off the distances. So if we let x, v, I be variables, where v is in v, in d, this is basically the locations that we, that's what phi does. It puts them in this, but let's call them variables. Then we can draw the following linear space. Here is the edges. Here we have D blocks, each with a vertices. Let's say that the number of vertices is n. So n blocks, sorry, D blocks. D copies, and in all of them you see the same thing. So let me do it in the first one. If we have here an edge ij, sorry, VU, ij is UV, and edge is UV, then in the we have what we need to look at is in the U location, in the V location. And what you write down is what we want the distance, so it's really the XU1 minus XV1 here, and XV1 here, minus XV1. And you do with 2 and 3 and 4. So it's a matrix, it's a symbolic matrix, yeah?
Not sure what happens in the different blocks.
1 changes to 2.
Okay.
Each dimension has its own variable. Okay, that's the coordinates of vertices in the first dimension, the second dimension. Okay.
So in the row of E, you'd have only 2 non-zero entries.
In every row, yeah, in each block, in every row, you have 2 non-zero entries.
Something and it's minus.
And yeah, something in its minus, absolutely. But anyway, it's a symbolic matrix of linear forms. Right? And what do we want to know? It turns out that, and it's simple, I mean, it's just from the equation that G is rigid if the rank, so let's see, I don't know, this will be LG, the rank of this linear space of matrices is at least, well, it says n choose d parameters, but there are d plus 1 choose 2 rigid motions, right, in this space, translations or rotation. So, and d minus. Anyway, there's a very simple, it's not singularity, it's rank, so we'll soon, I mean, anyway, define a rank, but it's what you think, so it's a rank of the symbolic matrix, so it's all the ranks except the, I mean, sorry, here we want that there will exist, it's like the non-singularity part. We want an embedding that will satisfy this. So we want a matrix, we want an assignment to the variables, which is just the embedding, that will give us a matrix of this rank. And of course, like we talked about in PIT, if there is an embedding, most of them will work, right? A random one will work, it's the same. So what is known about this? Here there is a really interesting open question. It's just this board for rigidity. It's from the 60s, I think. So in the case d equal 2 is empty. It's a polynomial time algorithm for the case of d equals 2.
They prove what?
For what? For what problem?
Rigidity. We did it in testing. I give you a graph.
Any graph?
Yeah. Yeah. So testing rigidity, namely testing the rank of linear matrices of this form, linear spaces of this form, is in P if the dimension is 2. If the dimension is 3, is open. And yeah, maybe I will not tell you, but Raz and I, so developed some extensions to this, but they don't solve the. Anyway, they don't get to. It's built on a paper of Lovas on understanding flats of matrices. So there are lots of linear spaces that arise in the study of flats of matrices. For some of them, you can give polynomial time algorithms, but they are related to this, but they don't solve the rigidity problem. So that's one I would love. It's a very special case, very structured matrices, right? Very structured linear spaces. We don't have deterministic algorithm. Of course, the usual probabilistic one works.
Is this related
Yeah,
Is this related to matrix rigidity in any way?
no,
Looks different.
no, not related to matrix rigidity. It's structure, it's really, when you want, this came up, this actually was defined by Maxwell, a physicist, James Clerk Maxwell in 1864. He was interested in statics, and yeah, he defined this problem.
For d equals 2, is there a sort of nice graph theoretic sort of character?
Thank you. Yes. Okay. Let me tell you the graph theoretic characterization. So it's a characterization of minimally rigid graph. From it, you can get a characterization of rigid graph, so that's sort of elegant. And from it, you can see, from this description, you can see that you basically can reduce it to matching or to float. Okay, so what's so it's like this. G is minimally rigid. For every subset S of the vertices, the number of edges in S is at most we are in the plane d plus 1 choose 2 is 3. So this is n times d minus d plus 1 choose 2. And so you need this for all sets, and for if S is V, then you have equality. Okay, so you have that's the minimum number of edges you need, and so yeah, it's sort of a matching question, sort of. You can think of analogous to a whole condition or something like this. Anyway, yeah, thanks. It's really cool, and there are other beautiful duality theorems of Novas and Yamini, but also only in the case of D equals 2.
And also for the original problem, that there's no hardness.
No, no hardness. It's a great question for any special case, actually. To think maybe it's complete for SDLT. Maybe this structured linear spaces are as hard as the I don't know any result like that. It's a very good question. Thanks.
Can you go back to that? Any minimal one has S equals to V? That is
No. When S equals to V,
then,
you have equality.
no, but you definitely need to require something else than an upper bound on the number of edges. I'm missing something.
It's minimally rigid.
If it's minimally.
Yeah, it's minimally rigid if and only if it's.
Yeah.
It's rigid, but removing any edge would not be rigid.
I see. So the if and only if is on the minimal.
Yeah.
Like,
the
okay,
minimum.
got it.
You can derive from this characterization for rigid graphs.
Okay.
Okay, yeah, so that's a problem I love, this D equals 3, and I tried, but yeah, anyway, it's beautiful, somewhat addictive. And the simple structure of this linear space is, it's amazing that maybe with a tree cannot handle such matrices. If you look at one block, what you see, I mean, if forget the variables, you basically see the incidence matrix of the vertices against edges, right? With some variables, it's the usual one. The last topic I want to talk about is the relation to non-commutative algebra and invariant theory. And since we talked about rank, let me define rank. So the rank of L, that's a linear space, is the minimum So maybe I should write it like this. It's the minimum R such that there exists matrices, I don't know. Spaces. In fact, let me make sure so L is a linear space, linear space of matrices. Rank of L must R if there exist matrices n, this is n by R, this is R by n, but they belong, their entries belong to the field of rational numbers. I mean, if we want to factor over the, or we want to factor matrix which is symbolic, which has anyway polynomials in it, we can. We need to allow rational functions in general, such as m and n. Okay, so it's the usual rank definition. This definition is completely equivalent to saying that every matrix in the space has rank at most R if the field is large enough. So, but I wanted to write it in this form. Okay, so this is just, you think of it as L as living in the field of rational functions, then you factor it into n by R by n as usual. Okay. Now, the question we asked there is a question about the rank of a linear space. Now, there is a, you know, so there are several reasons to do this, which I will not get into, but I'll tell you about some consequences. Is to consider, so far this is when the xi's commute. Until now, the variables I talked about were commutative variables. You can ask questions about the singularity of a matrix space or the rank of a matrix space. So you can look at this form L sum of AI xi when the variables commute and when the variables do not commute, and ask the same questions. Of course, the determinant doesn't make sense in the non-commutative case, but you can ask about inversion, you can ask about rank and so on. So the whole theory was developed first by mainly by Kohn. The first thing to ask is what is the analog of the field of rational functions in some variables? So in the exercise not commute. What is this field? So in the commutative case, it's just you close the polynomial, right? It takes a closure of the polynomial, and you get just every element here is actually a ratio of polynomials, a rational function. When you try to do this for non-commutative variables, you take non-commutative polynomials, that's easy to define. I mean, you just write monomials in all order. You try to close it to make it a field, this becomes a mess. I mean, it becomes a really complex object called the free skew field. And it's called, it's denoted this way. Anyway, it exists. I'm not going to define it, but I want to define ranks nonetheless. So this is in the commutative world. What is in the non-commutative world? We could say in the same way that non-commutative rank. Yeah, I'll motivate this at least to in connection to matrix spaces which are normal that we discuss the whole lecture in 5 minutes.
I think the Zoom is logged out.
He said, Sam said he'll monitor it. And you don't have to get him. I think maybe I can send him email.
The Zoom is fine.
Zoom is fine. Maybe it's our screen. Ah, so you see us, hear us?
Yeah.
Yeah, okay, we just don't see you. Okay. Could be worse. Okay. So you want to define the non-commutative rank of this. And you have the same definition. If there exists Mn as before, so that Mn equal that, and now they would live in this strength space, right? In this. The definition and it works, but the funny or the nice thing that happens, and that's a whole theory developed by Kohn, is that you can say much more. Some of the non-commutative world is more rigid. And this is the same definition, you can take it, instead of letting these matrices live in whatever weird world they live in, you can just replace this and put it just, namely just non-commutative. Polynomials. So you can just, it would be the same definition. In fact, you don't need polynomials, you need just a fine function. Somehow it's simpler. And because of this, I think I'm getting to the theorem that who asked me, I don't remember who asked me in the beginning about the permanent and theorem about matrix spaces that look like a whole theorem or chemical theorem. Ramon, right, Ramon. Here's a theorem of Kohn. So you can ask in particular about, well, we can do it in rank R, or we can do it about singularity. Non-commutative rank of R. It's not only if there exists change of variables, so now these are in PLN of F. You are not allowed to. These are constant matrices that you apply to the left and the right side of each one to the matrix space, so that you get what you get in the whole theorem. So here I'm drawing BLC. So it's another matrix space, pre and post matrix, just chain basis on both sides. And what you get is that a block of zeros, that's a whole block. So if you have A and B here, then A plus B. If you have this situation, of course, the rank cannot be more than R. And in the
simultaneously for everything?
Yeah, simultaneously for these are linear forms. So you just, right? I mean, we just apply this constant matrices to all matrices in our space, or to the basis, whatever you want. Right? So you have also linear forms sitting here. And these are constant zeros. Right? This prevents the rank from being bigger than R, right? Because it's a smaller rank of this. Yeah. So in the non-commutative case, it's an equality. I want to stress that it's not true in the commutative case. There are matrices, there are linear space. You probably know that in the commutative setting, so let me draw it here. You can have this famous matrix. C minus Z. This rank here. The rank is just 2. All matrices is a still symmetric matrix, so its rank is always even. So all matrices in this space have rank 2. But in this case, so you can, in particular, you cannot bring it to the, yeah, so also you cannot bring it to this form, despite the fact that it has a rank only 2. Okay, so what did I do? Let's see, I have 5 minutes. Just think what I want to do of that. Let's think what I want to do. Yeah, so let me just tell you theorem we proved about 5 years ago. Yeah. This handles the case that f is characteristic 0. And then it was done by Daniels. Subramaniam a year later in using very different methods for all f or large enough f. Is that NC rank, particular NC singularity, so somehow before that there were only exponential time algorithms. There were not even probabilistic polynomial time algorithm. So you can do this in polynomial time. And one thing that came out from work related to this by these guys and also by Dirksen and Markham is that non-commutative rank and non-commutative singularity have an expression in commutative terms. So there are structured linear spaces for which this algorithm is a polynomial time algorithm. And let me tell you what it is. So it's a theorem, I guess I can attribute it. Well, I can start from Hilbert because this really is the beginning of this, and these are degree bound for invariant rings. These famous papers from 1890 and 1893 are the papers that basically shaped a commutative algebra. These are the papers where he put the Null-Stahlendorf theorem, this final basis theorem. His motivation, I don't know, it's not well known, but what he wanted to arrive at the end is just prove that invariant rings of group actions have a finite basis. He was interested in a problem in invariant theory. For this, he developed everything. And of course, everything was used everywhere else besides this. But and then Dirksen, and then this IQS, and Dirksen Mark. So and by this I mean, so L is not, well, it's less than that. It's a non-commutatively singular in a non-commutative case. If and only if, I remind you that here, L is singular, and L is this, L is generated by the AI, the determinant of some AI. So in the non-commutative case, something very similar is true, if and only is the determinant of some AI tensor psi identity 0, where these are n by n matrices of variables. Of course, you can take this and just look at an n squared by n squared linear space, and you're asking whether it's singular or not. So the same tuple, the same generators of the linear space, can give rise to various linear spaces. I mean, we looked throughout, we looked only at this one, but we can look at this linear space. And it turns out that this linear space is, is singular if and only if the rank is, the tuple is non-commutatively singular. So that's a very different example of linear spaces we can solve in polynomial time the singularity problem for. And again, very, very different techniques. I mean, the techniques in these two papers are very different. This kind of an analytic or dynamical algorithm that goes along the orbit of a group action, which is actually defined by pre and post multiplying by linear transformation. This is an algebraic version, if you want, of the alternating path algorithm for matching, exported or extended to the case of to the linear algebraic setting. So they are very different. Anyway, they solve this problem. And the main import of these last two words here is to get the size of these matrices to be small, to be n by n. We knew from Hilbert that we could do it with finite size, some finite size. We knew from Dirksen that we could do it with exponential size. And his recent works, about 5 years ago, showed that this can go down to n. So somewhere between n and 1, the problem gets harder, right? We know for 1, we don't know how to solve it. Yeah, my time is up. Thank you. Questions from the audience too.
So the first theorem, like your version of the proof, it provides the matrices B and C.
No, but their algorithm does, ours does not. Even though it works with that. Yeah,
It works with it, but
yeah,
it doesn't.
no, so what the algorithm would find, if it is non-singular, it would find sort of the B and C that prove there's a sort of a certificate that proves that it is non-singular. But if it is singular, sorry, yeah, so you see, it doesn't give that. This is a proof of singularity. It doesn't generate proofs of singularity. It can generate proofs of non-singularity. Both questions are interesting. It turns out that you can generate proofs of non-singularity also by exhibiting some GLN matrices that put your linear space in a particular sort of isotropic position. Yeah, I can define it as somehow related to physics, to quantum information theory. But anyway, I have several talks recorded here on this subject, I mean, on this story. So you can watch or ask me whenever you want. Yeah.
A very stupid question, but you gave two examples two different things which come from the same object. Is there a relation between the rigidity and the rank of the linear matrices space? I'm asking because
This is the relation.
what?
The relation is written here. Rigidity. I mean, at least you are talking about this or that?
A relation between them.
No, I don't. To non-commutative.
The bad example that you gave of the space of matrices with rank 2,
Yeah,
which can be written like that, is exactly the matrices coming from the triangle.
it's yeah. So you're right. It's a
Has
good,
rank 2. So
good observation. It's a very good observation. So here is the. Yeah, so let me write, maybe I shouldn't write here because these people won't see it, but let me just, besides several examples of easy, easy by which I mean cases in P for linear matrix spaces for SDIT, let me write a couple more and I think I'll answer your question. So which are easy? SDIT, like rigidity in 2 dimensions. So a paper of Gurwitz tells you that, I mean, actually it was known before. So, so say that L is generated by A1. So one case is where the AIs are all of rank 1. If a space is generated by rank 1 matrices, then it's easy. Second case, and this is through the very complex, I would say, algorithm for method parity by Lovaas, is that if this is 2 and the AIs are antisymmetric. This is exactly the this is not exactly what gives the method. This is not. I don't see a connection. You're right that the matrices that arise in the matrix rigidity, in structural rigidity for D equals 2 look like this. In fact, the paper I mentioned with Orit Raz, you also have the you get more examples like this from antisymmetric tensor. And just maybe this is easy, but if all AI are PSD, for example. There are other examples. The really neat thing about this example, so I'm deviating from what you asked, but mention something about this. Maybe some of you know that to tell whether a linear space is spanned by rank 1 matrices is NP-hard. It's a famous result of Gurwitz, which relates to positive operators in quantum mechanics. They somehow they needed to know this. Nevertheless, this algorithm, in fact, already in Gurwitz's case, so there's an algorithm of Gurwitz that will test whether this is singular or not, given any basis, just assuming that there is a basis that is of rank 1 matrices. So you don't need to find them, it's hard to find them, but nevertheless, if you find them, then you can run a method intersection algorithm. But if you don't know them and you can't find them, a dynamic algorithm like what I mentioned there will still work and solve singularity in this case. More questions?
So Avi, I have a very naive question coming back to my original question. I know nothing about the algorithmic aspects of these things.
Just Ramon, I have a question to you. Is this a question? Is this a characterization you meant?
It's not exactly that one, but I can tell you later what I had in mind. Something.
Okay, so good. So ask you.
Permanent, right? Testing. No, the Frobenius-Koenig's theorem says that the permanent is 0 if and only if there is an R by S submatrix of zeros, such as R by S equals, I don't know.
Yeah, just like in the picture there. Yeah.
Okay, good. On the other hand, testing.
Let me just say, it's a theorem about single matrices, not about spaces of matrices.
Yes, yes, absolutely. I'm asking a very limited question. On the other hand, testing whether a particular bipartite graph has a matching, this can be done in polynomial time, right?
Yeah.
So that means that finding such a 0 submatrix of a 0-1 matrix can be done in polynomial time, because these two problems are
for one matrix.
Okay.
But through this algorithm, you can find through this algorithm that I just mentioned at the very end, this one that we just did 5 years ago, you can do it for a space of matrices. The only problem is that it doesn't solve the singularity problem that we want in commutative variables. It solves it in non-commutative variables. It doesn't solve any question about the permanent that I know.
No, I'm just trying to understand the analogy, right? Because, just let's think about the permanent, not about these more general questions, right? So we know the permanent, right? The permanent being 0 is equivalent to having a 0 submatrix of a certain size. We know it can be done in polynomial time. Is there any connection between the two? Can one view the algorithms that, that test for the existence of a bipartite matching as finding, are these algorithms searching for a 0 submatrix, or can we in any way think of them as searching for a 0?
Of course. The matching algorithms, the standard ones, alternating path will find a zero block, a whole blocker, if there is no perfect matching, of course. But maybe I should stress there's a big difference between testing whether the permanent is zero, which is an easy problem, and computing the permanent, which is a hard problem. So just zero testing is it.
So the reason I'm asking these questions, but I mean, it may be that this is not relevant because the theorem that I have in mind, not exactly this one, much less sophisticated, is about the reals, not about finite fields.
It would be great to have any algorithm for permanence over any field, except GF2, where it's the same as the determinant.
So if you think about the determinant of L of X, right, which is the question that you can write this, you can just expand this as a polynomial in the variables X, and the coefficients are going to be mixed discriminants. And the polynomial will be identically zero if and only if all of the coefficients are zero, right? So if all the mixed discriminants are zero, and testing whether a mixed discriminant is zero, there is a complete analog of the Frobenius-Koenig theorem, and that is the theorem I was referring to.
Yes, but you have to remember that there are exponentially many coefficients you want to test. The expansion of the determinant has exponentially many monomials.
I see.
So this is the main problem with any identity testing. I'll give you a polynomial. Of course, you can test with an identically zero polynomial by expanding and look at the coefficient.
And the permanent is special because it's diagonal matrices, and therefore the number of terms collapse.
It's what?
The permanent is the mixed discriminant of diagonal matrices.
Yeah, that's so, but
or there are many less terms in this polynomial, so it's much easier.
The permanent, you are talking about zero. Well, maybe we should continue it offline. So yeah, okay. Yeah. I'll see you here.
Explanation for what I'm missing. Yes. Okay.
Good. More questions. All right. Lunch.